We are welcoming you back into our lecture series on advanced hydraulics. We are in the third module on varied flows. So, if you recall from the last class, we had discussed on the higher order approximations that can also be used for solving the dynamic equation for gradually varied flow. One such method that we discussed was the fourth order Runge-Kutta method. We also had solved a demonstrative problem for the trapezoidal channel section using this fourth order Runge-Kutta method. So, we had done an extensive demonstration on that problem, and I hope you all have benefited much. You have understood the concept on solving that problem. If you recall the dynamic equation for gradually varied flow, you have seen that the equation, the dynamic equation as given here, it is a function of the spatial variable x and the depth of flow y, isn't it? So, that is dy by dx is function of x and y. This, according to your mathematical principle, you can integrate it in the following form, that is integral dy is equal to integral of f of x y dx, as you are taking a channel reach. Say if you are taking a channel reach between two sections 1 1 and 2 2. You take two sections like this. Here, if the depth is y 1, this is depth depth is y 2. Say this is at a location x 1, this is at a location x 2. Then the corresponding this integration can be provided in the following form. That can be again rearranged, and the solving is done usually in this particular form. So, the various forms you have seen already, how to evaluate y 2 based on the value given at y 1. So, this is called the step process. You have seen the direct step method, you have also seen the Runge-Kutta method. Today, we will see the standard step method for gradually varied flow computations. So, the standard step method, it is normally used for non-prismatic channels. The standard step procedure is used for non-prismatic channels. Say as given here, if there are two non-prismatic channels in a particular reach, say if this is the reach of the channel you are interested, or you can give it as del x also, it does not matter. And if you want to evaluate the flow properties in this particular non-prismatic channel, you use the standard step method. So, how do you evaluate them? How do you incorporate them? So, you know that say this is channel section 1 1 and this is channel section 2 2. Let us assume that the depth of the flow here as well as the velocity of the flow here, they all depend not only on the depth of flow, the velocity of the flow depends not only on the depth of the flow, it is also the function of x here, right, at which location of x it is. Similarly, here also this is a function of x, the flow properties are function of x, especially the if you evaluate the energy slope or the friction slope, you can see those things. So, they have all the hydraulic properties are, so in non-prismatic channel, hydraulic properties are functions of x and y, both x and y. So, in prismatic channels we have seen that most of the functions are properties of only the depth of flow y, but that is not the case in the non-prismatic channels. So, we have to use these things. So, what they do? Say if you have a reach of channel, a non-prismatic channel, they may conduct various field surveys at various locations. They conduct field surveys, maybe cross sectional survey as well as longitudinal survey along the reach, as well as the cross sectional details will be captured at various locations. Say this is section 1 this is section 2 this is section 3 Please note that this is the top view of a channel reach or non-prismatic or a natural channel that is being given here. So, you do cross sectional surveys, local field surveys are done, you measure the depth here, you measure the depth here, properties there, what are the cross sectional properties, all those things will be recorded. Once you record all those things, so now you know the distinct site locations of the channel reach. Between two stations, you can average the properties. So, suppose if all the properties are given here. Now, if you want to evaluate the flow depth at this location and this location like that, you can use the standard step method now. That is also a varied flow property, that is gradually varied flow. Using standard step method, you can evaluate the depth of flow. So, as we mentioned earlier, computations are carried out from a known location. Say at this location, if all the properties are given to you at this location, if all the properties are given to you, then using the step procedure, the step evaluation we have seen earlier in the equation. Say this is the step procedure. The same thing we are using, the same principles we are using here. So, in this thing, at section 2 to evaluate the depth of flow or even the velocity of the flow or even the discharge, as you know, it will be constant, because gradually varied flow we have suggested that discharge is constant throughout all the sections. So, discharge will be same, all these things can be evaluated. So, you use the known property from the left hand side and you evaluate the right hand side. So, how do I proceed now? So, consider the following channel section. Say if I have the following parameters, say if this is your channel depth, say at any depth z from the datum line. See, let me suggest what are these lines. First, let the bottom line be the datum line, and this thick line let me suggest you as the channel bed line, and the next line is the water surface line, and above one is the energy slope line. So, what are these quantities? Datum, channel bed and slope of the channel bed, you know it is given by the quantity S0, water surface line is given like this, and the slope of the water surface is given as SW, if you recall them. Energy slope line, if it can be evaluated, the energy quantities, if it is evaluated, you can easily give this quantity as yes, come on, SE or SF, right? We had given these things. Now, if at a location, if a particular location, if the channel bed of that location is at a elevation Z from the datum line, let the depth of flow be y at that location, and as this is a non-prismatic channel, the cross sectional details are coming into much prominence here, and not only that, the velocity, if you see that the velocity may not be uniform across the whole cross section. So, you may see you will be taking average velocity, and therefore, you may be incorporating energy correction factors and all. So, the velocity head at this location, it can be given as alpha v squared by 2g. So, if you add all these quantities z plus y plus alpha v squared by 2g, you are going to get the total energy. total energy H at any section is equal to the datum head called Z, small z, plus the elevation of water. Please note that why it is elevation of water. We are dealing with flow in open channels where the pressure is in hydrostatic condition. So, you have to note that we are not dealing with very high speed flows in such situations where you cannot use the hydrostatic assumptions. So, H is equal to Z plus Y plus alpha V squared by 2 G. So, this is the general total energy head equation you have already studied in this case. So, if I consider this as section 1 then the energy head at H 1 is equal to energy at section 1 is equal to H 1 is equal to Z 1 plus Y 1 plus alpha 1 V 1 square, like this we can write. Similarly, another section 2 if I take, and if that section is at an elevation Z2 from the datum line, the bed of that section is at an elevation Z2, then I can easily write H2 is equal to Z2 Y2 and this is alpha 2 V2 squared by 2G. So, Z2 plus Y2, so I will just give it at as mentioned earlier, H1 is equal to Z1 plus Y1 plus alpha 1 V1 squared by 2G. H2 is equal to Z2 plus Y2 plus alpha 2 V2 squared by 2G. Like this you can give the energy equations for the two sections. So, what do you get if these two sections are separated by a distance del x? If these two sections are separated by a distance del x in the bed, then we can write the following form. I can find, means you can see the water surface elevation from datum. I can just make another parameter now. I can just make another parameter such a way that the water surface elevation, this location at this particular from the datum line, this is now called as capital Z1. Similarly, this elevation, it is called capital Z2. Like this I can just identify two parameters. So, your Z1 is nothing but small z1 plus y1. Similarly, z2 is nothing but small z2 plus y2. From the following figure, can you guess certain quantities? Your z1 is nothing but z2 plus the channel bed slope is given, channel bed slope it is already given to you, that bed slope into this particular distance, that will give you the difference between z1 and z2, right. So, I can write z1 as z2 plus S0 into del x. You can easily write them. Therefore, your capital Z1 is nothing but Z2 plus S0 del x plus Y1. These are nothing but just manipulation or rearranging of the terms. There is no arithmetic things involved here. So, as you see here in this figure, your energy line, your energy, it is getting decreased at section 1 whatever total energy was there H 1, it is getting reduced to H 2 at section 2. So, what is the energy loss? What could be your energy loss? What could be the energy? H 1 minus H 2 will give you the energy loss, right? The various energy losses are loss of energy due to friction, that is, friction slope is SF. Based on that, you can evaluate loss of energy due to friction, and loss of energy due to eddy currents. As these are non-prismatic channels, there will be considerable eddy currents also. So, those things also causes loss in energy. So, and a loss of energy due to friction, I can give this particular term as HF and this particular term as HE. HF, the friction loss, it can be given as the friction slope into del x. So, we are going to take the average friction slope. So, between two sections, say in this case, this is section 1 and this is section 2. So, what is the friction slope here? SF1. This is here, it is SF2. Based on these two sections, so SF, you are going to take the average friction slope SF bar, that is given as SF bar is equal to half of SF1 plus SF2. So, you are going to take SF bar and you are going to multiply it with distance del x to give you the loss due to friction. Your eddy loss can be given by HE is equal to some coefficient, that is, say some coefficient KL into the change in velocity. Please note that the change in velocity that is causing them. So, of course, I have to use the energy correction factors also by 2G. So, the eddy loss is given by KL is a energy loss coefficient, eddy energy due to eddy currents and all. So, it is a parameter KL that can be experimentally found out. So, we are not going to going in detail about this particular parameter. So, it can be given by this following relationship, the eddy loss. So, please note that here we are going to take the magnitude in difference between the velocity. So, even as I mentioned, KL alpha 2 V 2 squared minus alpha 1 V 1 squared by 2G. This is given as a, so this is the modulus of this difference. So, even if V 2 greater than V 1 or V 2 less than V 1, your eddy loss is positive. So, there will be always eddy loss from the flow direction, from the upstream to downstream, whichever flow direction is there. Based on that, the eddy loss will be always positive, means it will be a loss of energy. You will not gain any energy due to those phenomena. So, eddy loss is always positive, that you have to note it. So, it is the magnitude of the difference that you are going to take. So, what does these relations suggest? You can see that Z1 plus alpha 1 V1 squared by 2g is nothing but equal to Z2 plus alpha 2 V2 squared by 2g plus friction loss plus eddy loss. Like this I can easily write it. So, you know what is Z1, what is Z2. Ultimately, what does this bring? This gives you the principle H1 is equal to H2 plus friction loss plus eddy loss. This is the fundamental principles which we have studied even in your undergraduate levels. So, this thing we have again come back into this thing. So, this relationship is the governing principle which we will be going to use for the standard step method. So, how you are going to use them? So, what is the first term? So, Z1 as we have mentioned, it is y1 plus small z1. So, you substitute all those quantities, z2 is equal to y2 plus z2. Here z1, if you recall them, this I can write it as y2 plus y1 plus z2 plus S0 into del x. Like this also you can write it. Substitute all these quantities. I can write for the two sections now, y1 plus z1 plus alpha v1 squared by 2g. This is nothing but y2 plus z2 plus alpha 2 v2 squared by 2g. Then the friction loss half into SF1 plus SF2 into del x plus eddy loss. Say, please note that based on the quantities I can write it plus, I can just simply write it plus Ke alpha 2 V2 squared minus alpha 1 V1 squared by 2g. This is the relationship you are going to get them. Just rearrange the terms, you will see that y1 plus z2 plus S0 into del x plus alpha 1 V1 squared by 2g is equal to y2 plus z2 plus alpha 2 V2 squared by 2g plus 0.5 into SF1 plus SF2 into del x plus the coefficient KL into mode of alpha 2 V2 squared alpha 1 V1 squared by 2g. So, these two terms gets cancelled off as I need not further elaborate. I can now easily so as you are aware that as you proceed according to the channel section, this is channel section 1 channel section 2 you as we already mentioned that this is a step procedure. So, properties of section 1 are assumed to be known. So, initially you have to be provided by a known section first, that is usually the control section. For excuse me. For example, in the M2 profile, where the M2, I hope you understand what is meant by M2 profile. In the M2 profile, in the upstream section, the control section can be provided, and based on that, where the normal depth is there, you can start evaluating the profiles. That is one method. So, here whichever section that is being given as control section, the properties are known to you, and the next section you are going into the next section and trying to evaluate the flow depth. So, therefore, at channel section 1 let us consider that all the things are known. So, I can rearrange the equation y 2 by keeping all the unknown quantities on one of the sides. So, alpha 2 V 2 squared by 2 g. So, it can be plus or minus, we are not sure based on the magnitude of the velocity. Plus 0.5 SF2 into del x minus, I am just writing it like this, y1 plus S0 into del x plus alpha 1 V1 squared by 2g minus 0.5 SF1 into del x plus or minus KL alpha 1 V1 squared, sorry V1 squared by 2g. Like this you can bring, that is, in this equation all the things has been brought into the right hand side of the equation. So, this theoretically speaking it should be some function of y 2, and for the exact function of y 2 mathematically it should be 0, right, because y 1 is a known quantity to here, known quantity for you here. So, all these things V 1 squared, SF 1, all those things are known to you, y 1 are known to you, and it is not an unknown quantity. So, this entire equation is function of y 2 only, y 2 is the unknown quantity here. Like this we can easily write it. So, f of y 2 which should be theoretically speaking should be a 0 value. So, what happens? So, theoretically f of y 2 is equal to 0. So, that means if your computation of y 2 is correct, then this relationship will give you 0, f of y 2 should be 0. But how will you evaluate f of y 2 on based on what criteria? So, we have to suggest some iterative procedure. We are suggesting iterative procedure to evaluate y 2. Say you are beginning, say giving some initial for the y 2, some value you are giving. Now, using this particular value of y 2, you are going to compute the function f of y 2, right. Once you compute this thing, check whether f of y 2 and whatever guess value you have given check whether f of y 2 0 is equal to 0. If not, then correct y 2. So, how will you correct them? How will you correct them? We are going to use Newton's method. So, this is a very famous method. So, in our standard step method, we are going to use Newton's method to improve the value of depth of flow. So, what is this method suggesting? It suggests that y2 at any s plus 1th iteration, this is nothing but equal to y2 of s, that is y2 in the previous iteration minus f of y2 using the s iteration value divided by the derivative of the function f of y2 at the position y2 is equal to y2 of s. Okay? This is how the Newton's method works. Now, how are you going to write f of y2? F of y2 is nothing but y2 plus alpha 2 v2 squared by 2g plus or minus kl alpha 2 v2 squared by 2g plus 0.5 SF2 del x minus y1 plus S0 del x plus alpha 1 v1 squared by 2g minus 0.5 SF1, then plus or minus KL alpha 1 v1 squared by 2g. So, whichever are there in this brackets, they are known values to you. So, you do no need to worry on those things, you can easily evaluate them by the y1 value which you are aware of that. So, your f of y2 is evaluated in this particular form, f of, or it is can be given in the following form, f of y2. Therefore, f dash y2 can be easily written as say 1 plus alpha 2 v2 by g dv2 by dy2, isn't it? Because you know v2 is function of depth y2, that is velocity at section 2 2 is function of the depth of flow at section 2 2. Similarly, plus KL alpha 2 v2 by g dv2 by dy2 plus 0.5. Now, you recall how using Manning's equation you have evaluated the energy slope SF or the friction slope SF. So, you can incorporate those things. So, you will see that energy friction slope SF is function of the depth of flow y. Therefore, this quantity can be written as 0.5 into the derivative of SF2 with respect to y2 into del x minus whatever these quantities are there in the bracket. Do you think they are function of y2? They are not. So, minus 0. So, this is how you evaluate f dash of y2. So, using these expressions, you substitute them in the Newton's method, improve on the iteration. You can start say whatever value of the whatever depth you had been provided for the section 1 you can give them as an initial guess for depth y2 and start the iteration. This due to this particular formation or whatever formula is there, your iterative process will converge or it will improve the value of y2, and you can continue the iteration till y2 gets converged to a particular value. Okay. So, I can suggest that. So, begin with a reasonable guess for y2 at the iteration number 0. You begin with a reasonable guess. Usually y2 for the iteration number 0 is taken same as the known value y1. So, you continue the iterations. Iterations are continued till some convergence is achieved. For example, the convergence criteria can be given as y2 in the s plus 1th iteration minus y2 in the s iteration. The modular, we are taking the mode only, y2 in the s iteration should be less than or equal to some convergence criteria value given, say epsilon. It can be 1 into 10 to the power minus 3, or it can be 1 into 10 to the power minus 4, or it can be 1 into 10 to the power minus 2, whichever problem according to the type of problem and all, it has to be appropriately used, or that is so that your computations are not getting exceeded too much. So, based on this particular formulation, we are just going to continue, or we are going to do, I am not going to extensively demonstrate the problem. The problem you have done for the direct step method. In the direct step method, we had given you the same problem, if you recall them. We had suggested a rectangular channel of width 2 meter and 50 meter long allows water to free fall. The channel is made of glass and the bed drops by 5 centimeter in the entire length. So, at the channel entrance, the depth is observed to be 0.5 meter. We have asked you to find the length of the gradually varied flow profile from the free fall brink to a section where the depth is 0.45 meter. So, here you use the standard step method for determining the flow profile. So, please note that the standard step method can be used for non-prismatic channels. Here we have given you a prismatic channel just to demonstrate the computations. You can use non-prismatic channels also if you have some problem, or if you have some ready-made problems with you already there for many rivers in India. You can evaluate this, you can use this method, this particular method, direct step method, standard step method to evaluate the flow or evaluate the profile. Okay. So, there are many standard softwares also that use the standard step method. For example, RS and all, they use these methods for evaluating the profiles. So, we are, for the demonstration purpose, we are using a prismatic channel here. So, if you recall, so this is the free fall, this is the brink, this is the brink, and at the brink, if you recall, it should be a critical flow. This is the normal depth of the flow at the channel entrance, right. So, normal depth, it is already given to you as 0.5 meter. Critical depth, you had evaluated the discharge. I am not going to compute it again. At that time, you had evaluated the discharge as 1.5203 meter cube per second. Subsequently, you evaluated the critical depth as 0.3891 meter. Then you came to know that this is an M2 profile, isn't it? You had also evaluated the bed slope to be S0 is equal to 1 into 10 to the power of minus 3 in this particular case. So, the flow is in this direction. Now, from the brink, this is your brink. So, this can be considered as channel section 1 You can go now into the upstream and find the location or find the section XX. Let me suggest it as section XX. We do not know which is this, we are at how many or how far is this section XX from the brink. We are not aware of that, but the question is we have to evaluate this or find this section where the depth of the flow is 0.450 meter. That is the question. So, how can you do these things? You can start from here, you can divide this entire portion say of 10 meters or 7 meters or 8 meters, 7.5 meters, like this. You can just divide these things, say del x is equal to 5 meters, or let me see in the table which I have given 10 meters. So, del x is equal to 10 meters. So, here x is equal to 0 0, here x is equal to 10, here x is equal to 20, like that. Just go on. So, we do not know at which location is the 0.45 meter depth is available. So, you proceed it in this way 10, 20, 30, try to evaluate the things. So, when you go for this section 2, you know the properties at section 1. So, y 2 in the 0th iteration is taken as y 1, which is the critical depth 0.3891 meter, fine. Then you will be using the relationship y 2 in the first iteration, this is equal to y 2 in the 0th iteration minus the function y 2 that has to be evaluated at y 2 is equal to y 2 at 0 divided by the derivative of the function f of y 2 at the location y 2 0, fine. So, how will you evaluate this function? For the function f of y 2, you require the velocity which is given by q by a. This you have to evaluate. You have to evaluate the energy slope or friction slope that is given by n squared q squared by a squared r to the power of 4 by 3. A you have to evaluate b into y, r you have to evaluate as a by p. On evaluating this for each value of y 2, each iterative value of y 2, you will be getting the corresponding iterative terms of f of y 2. You can have the corresponding derivative term f dash y 2, substitute them, like that you are going to evaluate them, fine. So, here for each section, say I am taking section 1 at 0 0, section 2 at 10 meters from the brink, section 3 at 20 meters from the brink, section 4 at 25 meters from the brink, like that you can just think. So, f of y 2 at any iteration, it can be given in the following form. You see here f of y 2 at any iteration s is equal to y 2 of s plus v 2 squared by 2 g plus 0.5 s of 2 del x plus or minus k L v 2 squared by 2 g minus subsequently the all other terms. These are self explanatory. You can evaluate the corresponding quantities from this, what is f dash y 2, that can be easily identified, isn't it? So, we have already shown you how to find f dash y 2. So, you can complete this problem now as a homework, because we have extensively explained to you the direct step method as well as the Runge-Kutta method, how the computations can be done. So, now at this stage you should be ready to do. We have given you the step how to evaluate the thing. You use them, try to compute the depth of profiles for these sections, okay, using the iterative procedure. So, f dash by 2 is given to you. So, we will be proceeding in this particular form. You can compute or you can calculate the depths. You can do it as an homework and submit to us later. So, the next topic which we are going to deal is the spatially varied flow. So, you have to understand what is meant by spatially varied flow. What is spatially varied flow? It is a type of non-uniform discharge that occurs in the channel due to the addition or deduction of water from the reach of the channel. Say, in this non-prismatic channel, if this is the reach of the channel that we are taking into consideration, between this reach, if certain quantities of water, if they are added into the thing, then the discharge from this section will be higher compared to this section, isn't it? So, that is causing changes in the flow. So, therefore, it is called as spatially varied flow. Similarly, if you are directing water from this reach, then the discharge at this section A1 and this section at A2 both are different. They are also called spatially varied flow. So, spatially varied flow, why we have to deal it separately compared to gradually varied flow? Why we have to deal it separately? Due to the addition of water or reduction of water, there will be much changes in the energy, or the energy and momentum are getting changed. So, you have to already use those correction factors. Not only that, you have to employ certain principles, so that as the discharge is not uniform, you cannot directly use whatever principles are used for gradually varied flow in such cases. There are two types of spatially varied flow. I can give it in short form SVF. So, those are flow with increasing discharge. So, within the reach, the discharge is getting increased. Say, it is getting increased due to addition of water. So, the discharge here will be more compared to section A1. Then the next one is flow with decreasing discharge. So, these two principles, these two types are already present. Now, what happens for flow with increasing discharge? As you have noted in the previous standard step method for non-prismatic channels and all, you have to incorporate eddy losses. Similarly, for flow with increasing discharge, for flow with increasing discharge, water from one side or one particular this thing, if water is flowing through a particular channel and if other discharges are coming into that, due to the mixing there will be turbulent action. So, turbulent mixings will be going on, that may create high energy losses, means the energy, that is energy differences will be there in such situations. So, those things need to be incorporated, and you may see that especially for flow with increasing discharge, it is very much difficult to use the energy equation for solving the problem. So, therefore, we normally adopt momentum equations for flow with increasing discharges. So, scientist Heinz had developed one of the first fundamental differential equation for spatially varied flow. Later on, scientist Favre had developed by incorporating certain friction terms and component of velocity terms in the axial direction, so as to develop the differential equations, governing differential equations for spatially varied flow. For decreasing discharge, you will see that they are mainly used for diversion flow problems, where the flow diversions are required, especially in dams where you need to divert water to a particular canal and all. For such situations they are used. In such problems you will see the energy loss is not that much, or it is not that much significant where it cannot be applied. So, you can still use the energy principles for solving flow having decreasing discharge. So, they are used for side spillways or flow diversion problems and all. So, next class we will be deriving the spatially varied flow dynamic equations. For that, some of the assumptions to derive spatially dynamic equation for spatially varied flow. We consider flow as unidirectional. So, in this age of computational fluid dynamics, where you can solve for all the 3 directions or n directions, this unidirectional is not much significant, but still we can apply them, so that the computations can be reduced. The velocity distribution is taken as uniform across the channel section, that is, you incorporate the velocity correction factor as 1 in the channel cross sections. Pressure is hydrostatic pressure condition as in other flows. Then the slope of the channel is relatively small. Manning's formula is used for evaluating friction slope and friction loss. Also, the air entrapment or entrainment in the channel, they are not being incorporated in the analysis. So, these assumptions are required when we derive the dynamic equation in the next class. So, based on the following things we have discussed, we can have a simple quiz today. The first question which I would like to ask to you is, can the standard step method be used for evaluating gradually varied flow profile for non-prismatic channels? Can the standard step method be used for evaluating GVF profile for non-prismatic channels? You can give the answer in a simple way. Your second question, how is Newton's iteration method used in standard step method for evaluating GVF profile? Newton's method, you should be aware that it is not only related to open channel hydraulics. So, you have to tell how that method can be used here. Your third question, whether the spatially varied flow is an uniform flow or non-uniform flow. What are the 2 types of spatially varied flow? Yes, you can use the standard step method for evaluating gradually varied flow profile for non-prismatic channels. In fact, this is the best method for evaluating GVF profiles. Many standard softwares like HEC, RS and all, they use standard step method for evaluating profiles. How is Newton's iteration method used in standard step method for evaluating GVF profile? Newton's iterative method, as it is being suggested, it gives improvement for the various iteration. So, it can be given as in the previous iteration whatever value is there by some function of y2 divided by df by dy2 at y2 is equal to y2 of s. Like this you can write it. So, Newton's procedure can be used for any function and these things we are using in our open channel hydraulics for evaluating gradually varied flow profile. So, whether spatially varied flow is an uniform flow or non-uniform flow. What are the two types of spatially varied flow? Spatially varied flow, it is a non-uniform flow. So, this is a non-uniform flow. Why this is a non-uniform flow is because your channel properties, it can change, or not only that, the discharge is getting increased or it is getting decreased. So, therefore, based on discharge also it is a non-uniform conditions prevail in that. So, it is entirely a non-uniform flow. The two types are spatially varied flow due to increase in discharge and spatially varied flow due to decrease in discharge. These are the two types of spatially varied flow available in general. So, the equations or the principles related to that we will be dealing in the next class. That way, today we conclude our lecture. Thank you.